Almost everyone alive has been told the same thing about how everything started. There was a beginning, we call it the Big Bang, and before it there was nothing, not even time. It is clean, it fits on a single line, and it rests almost entirely on one equation that, run all the way back, does not give an answer. It gives infinity. And infinity is not a discovery. It is the sound a theory makes when it reaches the edge of what it can describe. The oldest light we can see comes from 380,000 years after that moment, and it hangs across the sky like a wall nothing older can cross. So the truth is stranger than the textbook. No one has ever seen the beginning. We have only ever seen the wall, and 4 separate frameworks built by serious physicists all agree that something was waiting on the other side of it. Get comfortable. Hit subscribe if you're new here, because by the end of this, the word beginning will never feel quite so final again. Now, let's slowly ease into this. Part 1. The beginning you were taught. The story you were handed as a child went something like this. There was a beginning. We call it the Big Bang. Before that beginning, there was nothing, not even the word before, because time itself switched on at that first instant. Everything that exists, every particle, every force, every star you will ever see, unfolded from a single moment around 13.8 billion years ago. It is a clean story. It fits on a single line. And tonight, slowly and patiently, I want to walk you through why that clean little story is, at best, unfinished, and at worst, quietly wrong in a way that may change how you picture your own place in time. You have probably seen the picture that goes with the story. A point of brilliant light appears in the dark and rushes outward into everything. It is in the documentaries, it is in the textbooks. It is the image your mind reaches for when someone says the words, the beginning. Hold on to that image for a moment, because one of the strangest things I will tell you tonight is that nobody has ever seen it. Not once. Not with any instrument ever built. That glowing point of light is not a photograph. It is a drawing, an inference, our best reconstruction of a moment we cannot actually look at. We will come back to why that is and what sits in the way of our looking, but I want you to notice the gap now at the very start. There is the thing we say happened, and there is the thing we have actually observed, and those two things are not the same. Let me say clearly what the standard account claims, because it deserves a fair hearing before we start pulling at its threads. In the standard telling, the universe was once unimaginably hot and unimaginably dense, packed into a state far smaller and far fiercer than anything that exists today. From that state, it expanded and cooled. Particles formed, atoms formed, stars and galaxies assembled over billions of years. Run the film backward, and everything rushes together, hotter and tighter, until you reach the first instant, the moment we label time zero. In this picture, time zero is the edge of everything. Asking what came before is treated like a grammatical mistake. The way asking what is louder than silence is a kind of mistake. There is no before, the story says, because before is a word that needs time, and time had not started yet. I want to be honest with you about something, because this channel is built on being honest about what we know and what we only suspect. That framing, the one that says there is simply no before, is not a discovery. It was never something a telescope showed us or an experiment proved. It is an interpretation, a way of speaking about the edge of our theories that hardened over the decades into the way the story is told. And interpretations can be reasonable and still be wrong. The history of physics is largely a history of careful, reasonable interpretations that turned out to be the outside wall of a much larger building nobody had walked into yet. Consider how often the word beginning has misled us before. People once thought the edge of the known map was the edge of the world. Sailors believed that past a certain horizon there was simply nothing until someone sailed past it and found the horizon had only ever been a limit of seeing, not a limit of being. Astronomers once thought our galaxy was the whole of creation, a single island of stars surrounded by emptiness, until the smudges they had dismissed turned out to be other galaxies, each one as large as our own. Each time, the word edge meant the edge of our instruments, the edge of our reach, the edge of our imagination. Each time, we mistook the boundary of our knowledge for the boundary of reality. So when the modern story tells us that the Big Bang is the edge and there is nothing beyond, it is worth pausing and asking a simple, almost childish question. Is that the edge of the universe, or only the edge of what we can currently see and calculate? There is a temptation to treat that as an empty word game, the kind of thing that sounds profound at 2 a.m. and dissolves in daylight. I want to resist that temptation with you, because this question has teeth. If the beginning was truly the beginning, then we are the children of a single accident, a universe that switched on once and will wind down once, with nothing on either side of it. But if the beginning was a boundary, a handoff, a turning, then we are part of something with a history that did not start with us, and a structure that will not end with us, and the residue of that larger thing should be sitting in our data right now, waiting to be noticed. Those are not the same universe to wake up in. One is an isolated spark in an eternal dark. The other is a single chapter in a book whose earlier pages were written before we existed. And the difference between them is not a matter of taste or mood or comfort. It is a matter of physics, the kind of thing that gets decided by equations and, more and more, by machines pointed at the sky. That is why serious people spend entire careers here, and it is why I want to spend the next stretch of quiet hours on it with you. Here is what makes that question more than idle. The claim that the Big Bang is the absolute beginning rests almost entirely on one mathematical result, and that result is not a triumph of the theory. It is a breakdown of the theory. When you take Einstein's description of gravity and run it all the way back to that first instant, the equations do not hand you a tidy starting point. They hand you something far less comfortable, a place where the numbers stop making sense entirely. We will sit with that breakdown closely in a moment, because everything else tonight grows out of it. For now, just hold the shape of the problem in your mind. The single strongest reason we are told there was nothing before the Big Bang is that our best equation for gravity falls apart exactly there. And a falling apart equation is a strange thing to build a certainty on. You might reasonably ask, if the picture is shaky, why is it told with such confidence? Part of the answer is that the rest of the Big Bang story is genuinely, spectacularly successful. We can trace the expansion of the universe with great precision. We can measure the faint warmth left over from its hot early state. We can calculate how the lightest elements were forged in the first few minutes, and then go out and find exactly those proportions written across the cosmos. The model works, and it works beautifully for everything after that first opaque stretch. The confidence is earned almost everywhere. The trouble is that the confidence tends to leak backward, past the point where the evidence actually reaches, all the way to the first instant, where in truth we are no longer standing on observation at all. We are standing on the far end of an equation that has already told us it cannot describe what is there. What I want you to take from this first stretch of our walk is a single shift in posture. Stop thinking of the Big Bang as a wall with nothing behind it, and start thinking of it as a door we have not yet learned to open. The people who study this for a living, the ones with the equations and the satellite data and the careers built on this exact question, are not divided on whether the universe expanded from a hot, dense state. They agree on that. They are divided, quietly and seriously, on what that hot, dense state itself emerged from, and whether the question even has an answer we can reach. There are real papers, real mathematics, real researchers at real institutions arguing about what was here before. The question that most of us were told is meaningless is, in the actual scientific literature, one of the most alive questions there is. So tonight, we are going to do something the textbook version never does. We are going to walk straight up to the edge of the beginning, and instead of stopping there because the sign says no entry, we are going to look at what our own equations say is on the other side. We will find not one answer but four, each built by serious people, each pointing at something that existed before our universe began. We will find a fight over what may be fossils of an older cosmos hidden in the oldest light we can see. We will find a question so strange that it makes us wonder whether the word before means anything at all. And at the very end, we will find that for the first time in the history of our species, we are building machines that might actually let us listen past the wall. The beginning, it turns out, may not be the beginning, and the reason we were told otherwise starts with a single equation that breaks. Let us go and look at exactly how it breaks. Part 2. The equation that breaks. There is a moment in the history of an idea when its greatest strength turns, without warning, into its most honest confession. For our picture of the beginning, that moment lives inside Einstein's theory of gravity, and to understand what came before the Big Bang, you first have to understand the precise place where our best theory of the cosmos stops being able to speak. Let me start by giving that theory its due, because what is about to fail is not some flimsy guess. Einstein's general relativity is the most thoroughly tested description of gravity we have ever produced. It predicted that light would bend as it passed the sun, and it was measured bending by exactly the predicted amount. It predicted that massive objects spiraling together would send ripples through space itself, and a century later, we built machines sensitive enough to feel those ripples wash over the Earth. The satellites that tell your phone where you are standing have to correct their clocks using this theory, because time itself runs at a slightly different rate up where they orbit, just as Einstein said it would. When I tell you that general relativity breaks, I am not telling you it is unreliable. I am telling you that the single most reliable theory we have about space and time reaches a point where it turns to us and admits it can go no further. That point is the one we call the singularity. Here is how you arrive at it. Take the universe as it is now, expanding, galaxies drifting apart, and imagine running the whole process in reverse, like rewinding a film. Everything rushes back together. The space between galaxies shrinks. The temperature climbs. Matter packs tighter and tighter. So far, this is just the Big Bang story played backward, and the equations follow along happily for a very long way. But keep rewinding all the way to that first instant, and the equations do something disturbing. They tell you that the density of the universe becomes infinite. They tell you that the volume of everything shrinks to zero. They hand you a point of no size containing everything with a temperature and a density that are not large but literally without limit. You should distrust any answer that is infinity, and physicists distrust it too. Infinity is not a measurement. It is what an equation prints out when it has been pushed past the conditions it was built to handle. Think of a simpler example. If you calculate how the brightness of a lamp grows as you walk toward it, the math says the brightness rises without bound as your distance shrinks to zero. Taken literally, it claims a lamp becomes infinitely bright at zero distance. But that is nonsense, and everyone knows it is nonsense. What is really happening is that the simple formula stops being the right description once you are pressed against the bulb. The infinity is not a fact about the lamp. It is a signal that you have left the territory where your formula applies. The singularity at the start of the universe is the same kind of signal written across the whole of space at once. This is the single most important idea in everything we will discuss tonight, so I want to say it as plainly as I can. When an equation produces infinity, it has not found the answer. It has found the edge of its own validity. A broken equation is not a description of what happened. It is a confession that the theory cannot describe what happened. And so the singularity at the beginning of the universe, the thing so often presented as the origin point of all things, is better understood as the precise location where general relativity stops working and hands the problem to a theory we do not yet fully have. The people who proved how unavoidable this breakdown is were not fringe figures. In 1965, Roger Penrose proved a remarkable result about collapsing matter, showing that under very general conditions, gravity forces the formation of a singularity, a place where the known laws give out. A few years later, in 1970, Penrose and Stephen Hawking extended that reasoning to the universe as a whole, run backward. Their work showed that the singularity at the beginning is not some artifact you could dodge with a clever choice of starting shape. Within the rules of general relativity, given the universe we actually see, that breakdown at the beginning is forced. It is built into the theory. And notice the strange beauty of that. The theory itself, from the inside, is telling us exactly where it fails. It is handing us a map with one region marked here. The map runs out. What lives in that region is not nothing. That is the leap the standard story refuses to take. And it is the leap that the rest of this video is about. There is a difference, an enormous difference, between saying our best theory cannot describe what came before and saying, therefore, nothing came before. Those are two completely different statements, and confusing them is the central error in how the beginning is usually told. The first statement is honest. It says, we have reached the limit of one particular tool. The second statement is a claim about reality, a claim that there is genuinely nothing on the other side, and that claim does not follow from the first. It is smuggled in. The equations never said nothing is there. The equations said we cannot see from here with this tool. Imagine a sonar operator on a ship whose instrument can read the water down to a certain depth and no further. Below that depth, the readout dissolves into static. It would be one thing to say, we cannot map the ocean below this line with this device. It would be something else entirely to announce that the ocean has no bottom and no contents below that line, that the world simply ends where the sonar fades. The static is a fact about the instrument, not about the sea. When general relativity dissolves into infinities at the first instant, that static is a fact about general relativity. The question of what is actually down there, below the line where this particular theory can read, remains wide open, and it is answerable because there are other instruments, other theories, other kinds of signal that do not fade at the same line. Here is the quiet thing almost no one says out loud when they explain the singularity. The mathematics of physics does not contain a clause that says stop here, this is where description ends. The laws keep running. You can take the equations of quantum mechanics, which govern the smallest scales, and the equations of thermodynamics, which govern heat and density, and push them backward right through the region where general relativity alone falls apart. When you do, they do not return infinities. They return strange, finite, workable numbers. They describe a place. Several different ways of combining those laws describe several different places, and we will meet each of them. But every one of them agrees on the thing the standard story denies. The beginning was not the edge of being. It was the edge of one theory's vision. So we are left standing at a marked place on the map, the place where general relativity admits it cannot go. Most people are told to stop there and call it the origin. But the equation that breaks is not closing a door, it is pointing at one. And just past that door, our other theories are already speaking, already describing conditions, already insisting that something with structure and physics sat where the standard story sees only an absolute beginning. The first thing standing between us and that door is not a theory at all. It is a wall of light, the oldest light in the universe. And to understand what is behind it, we have to understand why we cannot see through it. That is where we go next. Part 3. The Wall of Light. In 1965, two engineers pointed a strange horn-shaped antenna at the sky and accidentally heard the universe being born. They were not looking for the beginning of everything. They were trying to get rid of an annoying hiss. Arno Penzias and Robert Wilson worked at Bell Laboratories, and they had a sensitive radio antenna that they wanted to use for careful measurements. The trouble was a faint background noise that would not go away. It came from every direction in the sky. It was there during the day and during the night. It was there in every season, no matter where they aimed the instrument. They checked everything. They suspected their equipment. They famously cleaned out a pair of pigeons that had nested in the antenna and scrubbed away what the birds had left behind, thinking that might be the source. The hiss remained. It was the same from every patch of sky, steady and uniform, and it simply could not be removed because it was not coming from their antenna or their city or even their galaxy. It was coming from everywhere at once because it was the cooled-down afterglow of the early universe itself. What they had stumbled into is now called the cosmic microwave background, and it is the oldest light that any instrument can ever detect. To understand why it matters so much for our question tonight, you have to understand what the early universe was actually like, because it was not the clear star-dotted darkness we see when we look up now. For the first stretch of cosmic history, the universe was a fog. It was so hot and so dense that ordinary atoms could not even hold together. Electrons, which normally orbit quietly around the centers of atoms, were instead torn loose, roaming free in a charged soup. And light cannot travel far through a soup of free electrons. A particle of light, a photon, would move a tiny distance and then be scattered, absorbed, knocked sideways almost immediately. The early universe was, in plain terms, opaque. It glowed like the inside of a star, but you could not see through it, because light could not cross it without being thrown off course again and again. Then something gentle and enormous happened. The universe expanded, and expansion cools things down, the way gas cooling lets a fog settle. After about 380,000 years, the temperature dropped low enough that the roaming electrons could finally be captured and held by atomic centers, settling into the first stable, neutral atoms. This event has a quiet name, recombination, and the moment it happened, everything changed for light. Suddenly, there were no more free electrons clogging the way. The fog cleared, and the light that had been trapped, bouncing endlessly in that hot soup, was set free all at once to travel in straight lines across the universe. That release of light, from the moment the cosmos turned transparent, is the cosmic microwave background. It has been traveling ever since, for more than 13 billion years. Now here is the part that touches us directly, sitting here tonight. That light was released as a fierce glow, the radiance of a universe still thousands of degrees warm. But over the billions of years it has travelled, the universe has kept expanding, and that expansion has stretched the light along with it, drawing its waves out longer and longer, draining its energy, cooling it down. What began as a brilliant glow has been stretched all the way down into faint microwaves, the same part of the spectrum your kitchen appliance uses, but unimaginably weak. Today that light fills all of space at a temperature of just under 3 degrees above the coldest possible cold, a little under 2.73 degrees on the absolute scale. It is the faint hiss Penzias and Wilson could not remove. It is, quite literally, the leftover warmth of the moment the universe first became clear. When later satellites mapped this ancient light in fine detail, they found something that should give you a small chill of wonder. The temperature of that glow is the same in every direction to about 1 part in 100,000. Picture an ocean that, measured anywhere on Earth, came out to within a fraction of a degree of every other point, top to bottom, shore to shore. That is how smooth the oldest light is, and yet it is not perfectly smooth. There are tiny variations, hills and valleys in the temperature far smaller than 1,000th of a degree, and those almost imperceptible ripples are the seeds from which everything grew. The denser spots pulled in more matter by gravity, and over billions of years those faint patches became the galaxies, the clusters, the great structures that fill the sky tonight, including the one that holds our own sun. So the oldest light is not only a barrier, it is a kind of baby photograph of the universe, the earliest portrait we will ever have, with the first hints of structure already faintly drawn in it. But notice what even this most perfect of measurements cannot do. It can show us the universe at 380,000 years old in astonishing detail and not one instant earlier. The portrait is gorgeous, and it stops exactly at the wall. And this is where we run into the wall. That light, the cosmic microwave background, is the oldest thing any telescope can ever show us, and it is not the beginning. It is a snapshot of the universe at 380,000 years old, the moment the fog lifted. Everything before that moment is hidden behind it, because before that moment the universe was opaque, and no light from earlier than that can reach us. It was all scattered and absorbed before it could ever begin its journey. So, when we point our finest instruments at the sky, the Planck satellite that mapped this ancient light with extraordinary care, the great observatories that have studied it for decades, they all reach the same barrier. They can show us the universe at 380,000 years old, glowing softly from every direction, and then the picture simply stops. There is a wall, and the wall is made of the last light that could escape. I want you to feel how genuine this barrier is, because it is easy to underestimate. This is not a limit we can engineer our way past by building a sharper lens or a larger mirror. The James Webb Space Telescope, one of the most powerful eyes we have ever lifted into space, can look back to galaxies that formed a few 100 million years after the beginning, and that is a staggering achievement. But it will never, ever see the first 380,000 years, and neither will any successor that works by gathering light. The opacity of the early universe is not a smudge on the lens. It is a property of the cosmos itself in that era. No instrument that detects light, of any kind, optical, radio, infrared, will ever cross that wall, because the light we would need was never able to leave. So let us return to the picture from the very beginning of our walk, the brilliant point of light exploding outward, the image everyone carries for the Big Bang. Now you can see clearly why I said no one has ever seen it. The oldest thing we can see is not the explosion. It is a wall of soft, cold light hanging at 380,000 years, and everything earlier, the first minutes, the first second, the first instant, the entire region where general relativity broke down, all of it lies on the far side of a barrier that ordinary light cannot pierce. Every image you have ever seen of the actual beginning is a reconstruction, a careful drawing built from theory and from clues, not a photograph. The photograph stops at the wall. You might think this is the moment where the story has to end, where we throw up our hands and say the rest is forever hidden. That is certainly how it can feel. The oldest light we have stops short of the beginning. The equations break at the beginning, and between the two sits a wall we can never photograph. It would be reasonable to conclude that what came before is simply beyond all reach, a sealed room with no door. But that conclusion would be wrong, and it would be wrong for a reason that is genuinely thrilling once you see it. The wall stops light. It does not stop everything. There are other messengers, and there is the quiet power of careful inference, and together they let us say a great deal about what sits on the far side of a barrier we will never see across. The wall is real, but it is only a wall for light. What gets through is where the real story begins, and that is exactly where we are going next. Part 4. The wall is only a wall for light. There is a quiet assumption hiding in the idea that we cannot see past the wall, and once you notice it, you cannot unsee it. The assumption is that seeing and knowing are the same thing. They are not. We know a great many things we have never seen, and the early universe, it turns out, is one of them. Let me start with the simplest version of this point, because it dissolves a lot of the despair. Consider the center of the sun. No probe has ever traveled there. No instrument has ever sat in the core of a star and sent back a reading. The temperatures and pressures there would destroy anything we could build long before it arrived. By the standard of direct seeing, the core of the sun is as hidden as the early universe. And yet I can tell you, with real confidence, that the center of the sun is around 15 million degrees, that it fuses hydrogen into helium at a known rate, that it has a particular density and pressure. We know these things not because we looked, but because the laws of physics are consistent, and we can calculate what the inside of a star must be doing to produce the outside we observe. The inside is hidden from sight, but it is not hidden from physics. Inference is not ignorance. It is knowledge arrived at by a different road. This is the first thing that gets through the wall, and it is not a particle at all. It is the simple, stubborn fact that the equations of physics do not switch off where our telescopes do. The laws that govern how matter behaves at a certain temperature and density are the same laws whether or not a photon can escape to tell us about it. So, we can take what we know about the universe just after the wall, the universe we can see, and run the physics backward into the hidden region, calculating the temperature, the density, the behavior of matter, second by second, back toward the beginning. We have done this for decades. It is how we know the lightest elements were forged in the first few minutes, a prediction we then confirmed by measuring those exact proportions in the oldest stars and gas. The first few minutes are behind the wall, unseeable, and yet we have a detailed, tested account of what happened in them. The wall blocks light. It does not block calculation. But inference from known physics has a limit, and I want to be honest about it, because honesty is the whole point of doing this carefully. Calculation can only carry you as far as your theory is trustworthy. As long as we are dealing with conditions our physics has been tested against, the calculations are solid. But the closer we push toward that first instant, the more extreme the conditions become, until we reach the region where general relativity broke down, the region we talked about earlier. There, our calculation alone is no longer enough, because the theory we are calculating with has reached its own edge. So, if inference were our only road past the wall, we would still be stuck at that edge, able to describe everything up to the breakdown but no further. We would need something else. We would need an actual signal, a real messenger that left the hidden region and travelled to us untouched, carrying information that light could never carry. That messenger exists, and it is one of the most wonderful facts in modern physics. It is the gravitational wave. A gravitational wave is a ripple in the fabric of space itself, set off when massive things move violently, and it has a property that makes it perfect for our purpose. Unlike light, a gravitational wave is barely affected by matter. It does not get scattered and absorbed by a soup of free electrons the way light does. It passes through almost everything as if the matter were not there. Right now, gravitational waves from distant collisions are passing through the Earth, and through your body, and through the walls around you, almost completely unimpeded. The dense, opaque fog of the early universe, the fog that trapped light and built the wall, would have been nearly transparent to gravitational waves. They could cross it as if it were clear glass. Think about what that means for our question. A gravitational wave produced in the first fraction of a second after the beginning, in the very region behind the wall, in the very era where light was hopelessly trapped, would have sailed straight through the fog, straight through the wall, straight through more than 13 billion years of expanding space, and it would still be arriving today. It would be faint, stretched and weakened by all that cosmic expansion, but it would be carrying the imprint of physics from a time and a place that light can never reach. Where light gives us a wall at 380,000 years, gravitational waves, in principle, give us a window all the way back to the first instant. They are a signal in a different language, written in the geometry of space rather than in light, and they were never stopped by the thing that stops everything else. This is not a daydream. It is the entire reason the next generation of gravitational wave observatories is being built. And we will spend real time later tonight on those machines, because they are the instruments that may finally let us read what is behind the wall. For now, I want you to sit with the reversal that has just happened. We began this stretch of the walk feeling sealed out, facing a barrier that no telescope can cross, an oldest light that falls short of the beginning. And we are ending it with two separate ways through. The first is calculation, the quiet power of laws that do not stop where our seeing stops. The second is a messenger that ignores the wall entirely, carrying news from before the oldest light was even set free. So the picture is not a sealed room. It is a room we cannot photograph, but can still measure, still calculate, still listen to with the right kind of ear. And when we do, when we push the physics back through the wall and ask what was there in the hidden region just before our universe began, we do not get silence. We get answers, several of them, each built by serious people using real mathematics, and every one of them describes a before. Not nothing, something. The next 4 parts of our walk are those 4 answers, 4 different pictures of what sat on the far side of the beginning. The first of them takes the very moment where general relativity broke down, the singularity, the place of supposed infinities, and replaces it with something no one expected, not an edge, a bounce. Part 5. The bounce. Imagine compressing a spring. You press it down, and it resists, and the harder you press, the harder it pushes back, until you reach a point where the coils themselves are touching, and the spring simply will not be compressed any further. There is a flaw. The structure of the spring sets a limit below which it cannot go. Now hold that image, because the first picture of what came before the Big Bang says that space itself has a flaw like that, and when you try to crush the universe down past it, the universe does not vanish into a point. It rebounds. To see how this works, you have to know about a quiet disagreement at the foundation of physics. We have 2 magnificent theories of reality, and they do not get along. One is general relativity, which we have already met, and which describes space and time as a smooth, continuous fabric that can bend and stretch without limit. The other is quantum mechanics, which describes the world of the very small, and which insists that nature comes in tiny, discrete units, that energy and matter are grainy rather than smooth when you look closely enough. These 2 theories are each extraordinarily accurate in their own territory. But at the beginning of the universe, where everything is both extremely massive and extremely small, you need both at once, and they contradict each other. General relativity says space is smooth and can be crushed without end. Quantum mechanics suggests that almost nothing in nature is truly smooth and endless. The breakdown we saw earlier, the singularity, is in large part this contradiction coming to a head. One serious attempt to resolve that contradiction is called loop quantum gravity, and its central idea is as bold as it is simple. It takes the graininess of the quantum world and applies it to space itself. In this picture, space is not a smooth sheet that can be divided forever. It is woven from tiny units, a network with a smallest possible size, below which the very idea of space stops meaning anything. That smallest size is unimaginably small, around 10 to the minus 35th of a meter, a length so tiny that compared to it, a single atom is larger than the whole solar system is to you. But the crucial thing is not how small it is. The crucial thing is that it is not zero. There is a flaw. Now watch what that flaw does to the beginning. In 2001, a physicist named Martin Bojewald took the equations of this theory and ran them backward into the early universe, into the very region where general relativity falls apart. He was not trying to invent a new origin for the cosmos. He was testing whether the framework held together under the most extreme conditions imaginable. And it did more than hold. It produced something the old equations never could. As he ran the universe backward, the contraction grew and grew, the density climbed, everything crushed inward, exactly as before. But when the compression reached that smallest possible scale, the floor woven into space itself, it stopped. The graininess of space resisted, the way the touching coils of a spring resist. There was no point of infinite density. There was no singularity. Instead, the collapse reached the floor and reversed. The crushing became expansion. The universe bounced. Let me make sure the meaning of that lands, because it is quietly staggering. In this picture, what we call the Big Bang, that initial moment of fierce outward expansion, was not the creation of everything from nothing. It was a rebound. Before it, there was a universe, and that universe was contracting, falling inward for a very long time, collapsing toward the same floor. When it reached the floor, it could go no further, and the collapse turned into the expansion we now find ourselves riding outward on. The energy that had been driving the contraction became the energy driving our expansion. The beginning was a transition, a handoff, the death of one universe's collapse becoming the birth of another universe's growth, our universe. I want to take you down into that moment, slowly, because it is worth feeling rather than just hearing. Picture a universe before ours, in its final age, contracting. Galaxies that had once drifted apart are now streaming back toward one another. The night sky in such a universe, if anyone were left to see it, would be brightening, the light of approaching galaxies shifting toward the blue and then toward a fierce white as everything rushes inward. The space between things shrinks. The temperature climbs past the point where stars can exist, past the point where atoms can exist, until all of matter is dissolved into a single searing density. And still it falls inward, faster, hotter, tighter toward the floor. Then, at the smallest possible scale, in the space of less than an instant, the fall meets the limit it cannot cross. The compression shudders, it stops, and it reverses. The inward rush becomes an outward rush. The dying universe, at its tightest and most violent moment, becomes the first instant of a new one. That reversal, that exact turning point, is what we have been calling the beginning of time. It was not a beginning, it was a bounce. There is a further question buried in this picture, and it is the kind of question that keeps physicists up at night in the best way. If a universe came before ours and bounced into it, did anything survive the crossing? Does any trace of that earlier cosmos make it through the bounce and into ours? Or does the violence of that turning point erase everything, leaving our universe to start fresh with no memory of what came before? The honest answer from the mathematics is somewhere in between, and it is fascinating. The bounce does not preserve everything. Whatever fine detail the previous universe had, the arrangement of its galaxies, the particular shapes of its structures, would almost certainly be smoothed away in the crushing passage through the floor. But some general properties, certain features of the quantum state of space itself, might carry across, leaving a faint imprint on the conditions our universe began with. We do not yet know how large that imprint would be, or whether we could ever measure it. But the very fact that the question is well posed, that we can ask in a precise way what a previous universe might have whispered into the starting conditions of ours, is something the old story of an absolute beginning could never even frame. You cannot ask what a beginning inherited. You can ask what a bounce carried through. Now, the natural objection: is this just a clever story, or is there real mathematics behind it? The mathematics is real, and it is specific, and here is the detail that matters most. Where general relativity gave us infinity, an answer that is no answer, loop, quantum gravity gives us a number. The density at the bounce is enormous, almost beyond comprehension, something close to what physicists call the Planck density, a value with around 96 zeros after it when written in ordinary units. That is an absurd, towering number, but it is a number. It is finite. And a finite number is a completely different kind of thing from an infinity. An infinity is a wall, a place where the theory has given up. A finite number is a place you can stand, a condition you can describe, a starting point for calculation rather than the end of it. The bounce replaces the place where physics broke with a place where physics still works. I will not oversell this to you, because that is not what we do here. Loop quantum gravity is one serious attempt at combining the two great theories, but it is not the only one, and it has not been confirmed. Another major program, string theory, approaches the same problem differently and gives a different picture, and we will meet a version of it later tonight. The energies involved in the bounce are so far beyond anything we could ever produce in a laboratory, around 1 trillion times beyond the reach of our most powerful particle accelerators, that we cannot simply go and test it directly. So the bounce sits in the scientific literature, mathematically careful, reviewed by other physicists, neither proven nor refuted, and strangely absent from the public story of where we came from. Most people have never heard that our best tested ideas, pushed through the breakdown, can produce an entire universe before this one. But they can. The equations did not stop at the beginning. They went through it, and on the other side they found not nothing, but a previous cosmos falling toward the floor we rose up from. Something was here before us, not as a metaphor, as a result, written in mathematics, from a serious attempt to describe the most extreme moment there is. And if that idea unsettles you, hold steady, because the next picture goes further. It does not just put a contracting universe before ours. It puts an entire, complete cosmos before ours, one that lived a full life, grew old, and died. And it claims that the corpse of that universe is hiding, right now, in the oldest light we can see. That idea comes from a man who won the Nobel Prize, and it is where we go next. Part 6. The universe before this one. A man who has spent his life proving difficult truths about black holes looked at the far future of our universe, the cold and empty end of all things, and saw in it the face of a beginning. His name is Roger Penrose, and the idea he built is one of the strangest and most carefully reasoned pictures of what came before the Big Bang that anyone has ever proposed. You should know who is making this claim, because it matters. Roger Penrose won the Nobel Prize in Physics in 2020. He did not win it for the idea I am about to describe. He won it for the earlier work we already met, the mathematical proof that black holes are a genuine and unavoidable prediction of general relativity, the same singularity reasoning from 1965. This is not a man wandering in from outside the field with a wild guess. This is one of the people who built the mathematical foundations the field stands on. So when he proposes something that sounds, at first, almost impossible, it is worth slowing down and following the argument, because the argument is the opposite of careless. His idea is called conformal cyclic cosmology, and the name is technical, but the reasoning underneath it is something you can follow without any mathematics at all. It begins not with the beginning, but with the end. So let us think, for a moment, about how our universe is going to die. Right now, the universe is full of structure, stars burning, galaxies turning, light everywhere. But that is a phase, and it will pass. The stars will, one by one, burn through their fuel and go dark. Galaxies will drift apart as space keeps expanding. Over timescales so long that the numbers stop feeling like numbers, even the matter itself will be swept up, and the great black holes that sit at the centers of galaxies will swallow what remains. And then, over a span of time almost beyond writing down, even those black holes will slowly evaporate, leaking their mass away as faint radiation until they too are gone. What is left, at the absolute end, is a universe with almost nothing in it that has mass, just light, just radiation, spreading thinner and thinner through an enormous, dark, still expanding space. It is worth letting the timescales here settle over you, slowly, because they are part of why this idea feels so strange and so calm at once. The age of the universe so far, around 13.8 billion years, is the largest span most of us ever try to picture, and it is already almost too large to feel. But the far future Penrose is describing dwarfs it beyond any comparison. The last small stars will still be quietly burning hundreds of billions of years from now. The era when galaxies have drifted out of each other's reach lies trillions of years ahead. And the slow evaporation of the great black holes, the final disappearance of the last massive things, unfolds over spans so long that you would have to write a 1 followed by a great many zeros just to count the years. Against numbers like that, the entire history of stars and planets and life is a brief flicker near the very start. What Penrose asks you to do is to stand at the far end of all of it, in the cold and the quiet, long after the last light of the last star, and to notice that in that emptiness, where nothing is left to measure size or mark time, the universe quietly loses the ability to tell the difference between its own enormous end and a brand new, tiny beginning. Here is where Penrose makes the turn that no one else made, and it is a turn about the strange importance of mass. Mass, he points out, is what lets the universe keep time and keep scale. Massive particles are what allow you to build a clock, because a clock needs something that changes in a regular way, and you need mass for that. Massive things are what let you measure size, because to say something is large or small, you need a ruler, and rulers are built from matter. But in that final state of the universe, when all the mass has decayed away and only massless radiation is left, there are no clocks left to tick and no rulers left to measure with. And Penrose argues that in such a universe, the very ideas of large and small, of a long time and a short time, stop having any meaning. There is nothing left that could tell the difference. A universe with no mass has lost the ability to define what size even is. Now follow the consequence, because it is astonishing in its logic. If size no longer has any meaning in that final mass-free state, then the difference between unimaginably large and unimaginably small simply dissolves. And the cold, empty, infinite future of a dead universe, where scale has lost all meaning, turns out to have the same underlying mathematical shape as the hot, dense, tiny beginning of a new one, where scale had not yet come to mean anything either. Penrose argues that these two states, the end of one universe and the beginning of the next, are not merely similar. They can be mathematically identified with each other. The infinite, frozen future of one cosmos becomes, by a change in how scale is measured, the fiery birth of the next. He calls each such cosmos an aeon. The end of one aeon is the beginning of the next. The universe does not bounce, in this picture, and it does not collapse. It simply continues, the way one chapter continues into another, with what we call the Big Bang being the surface where a dying universe's geometry passes seamlessly into a newborn one's. Let me say plainly what this means, because it is a claim of remarkable scale. Before our Big Bang, in this picture, there was an entire previous universe. It was not a brief contracting phase. It was a complete cosmos that lived through its own long history. It had its own stars, its own galaxies, its own era of light and structure. Its stars burned out. Its black holes formed and grew and, after almost endless ages, evaporated away. Its last light spread out across its enormous, darkening space. And then, as the last of its mass decayed and scale lost its meaning, that universe's frozen, infinite future became our blazing beginning. We are not the first. We are the latest aeon in a sequence that may stretch back without end, each universe handing on to the next across the surface we mistake for the start of everything. That alone would be enough to keep you awake. But Penrose did something that separates a good story from a piece of science. He asked whether such a previous universe would have left any trace, anything we could actually go and look for. And he realized it should have. In the previous aeon, there would have been black holes, because every universe with matter eventually makes them. And those black holes, as they slowly evaporated and as they collided and merged, would have released tremendous bursts of energy. Penrose argued that those bursts could pass through the transition between eons and leave faint marks in the oldest light of the next universe, our universe. Specifically, he predicted they would appear as gentle circular patterns written into the cosmic microwave background, the same ancient light we met at the wall. Rings, slightly smoother and quieter than the radiation around them, sitting in the sky like ripples frozen on a pond. Fossils, if you like, of a universe that lived and died before ours was born. I want you to notice how far we have come from the textbook beginning. We started with a clean story that said there was nothing before, that the question itself was meaningless. And now we have a Nobel laureate telling us not only that an entire universe preceded ours, but that it left physical evidence we can search for in data we already possess. That is the difference between speculation and science. Speculation says maybe something was there. Science says here is what it would have left behind, here is where to look, and here is what the data should show if I am right. Penrose pointed at a specific feature in a specific place and said, "Go and check." And so people did check. They went into the maps of the oldest light, looking for his rings. What they found, and the fierce argument that broke out over whether it was really there, is one of the most revealing fights in modern cosmology, and it is exactly where we are going next. Part 7. The Fossils in the Oldest Light. In 2010, Roger Penrose and a physicist named Vahe Gurzadian announced that they had found them. Not a prediction, not a model, an actual signal sitting in the oldest light in the universe that they claimed was the fingerprint of a cosmos that existed before ours. They had gone into the maps of the cosmic microwave background, the data from the satellite that had charted that ancient wall of light across the whole sky. And they reported finding circles, concentric rings, regions where the temperature of the background light varied less than it did everywhere else, arranged in patterns that the standard story of the universe gave no reason to expect. Quiet rings in a noisy sky. Their interpretation followed directly from the idea we just walked through. These rings, they said, were the marks left by enormous events in the previous eon, the collisions and mergers of giant black holes, whose energy had crossed the boundary between universes and printed faint circular patterns into the light of ours. If they were right, then humanity was looking, for the first time, at the physical remains of a universe older than our own. You can imagine the weight of that claim. And here is where the story becomes a real lesson in how science actually works, because the response from the rest of the field was not applause, and it was not silence. It was fast, it was technical, and it was sharply critical. Within weeks, several independent groups of researchers published their own analyses, and they reached a uniform conclusion. The rings, they argued, were not special. The problem was subtle, and it is worth understanding. To say a pattern is surprising, you have to compare it against what an ordinary, patternless universe would produce by pure chance. Penrose and Gurzadian had made that comparison, but the critics said they had made it wrong. When you generate simulated skies using the standard model of the universe, the ordinary kind, with no previous eon at all, those simulated skies produce the very same kind of concentric rings, just from random fluctuations. One group tested the data using 5 different statistical methods, and none of them found that the real rings were any more remarkable than the rings you get from pure chance. The signal, they concluded, was not a fossil of an older universe. It was the ordinary texture of randomness, and the human eye, and the human hope finding shapes in it. That sounds like the end of the idea. But Penrose did not concede, and his counter-argument is the part that keeps this from being a simple story of a claim refuted. He and Gurzadian pushed back on the very simulations the critics had used. Those standard simulated skies, they argued, are themselves built on a set of assumptions about how the early universe behaved, assumptions about the pattern of fluctuations baked into the standard model. If your comparison skies already assume the standard story is the whole story, then finding that the data matches them does not actually prove very much. You have, in a sense, assumed your conclusion before testing it. The comparison, Penrose argued, was circular. This is not a dodge. It is a real and recognized difficulty in this kind of work. The problem of how you build a fair null comparison when the thing you are comparing against is itself a model full of assumptions. And it has never been cleanly resolved. The argument did not end. It evolved. By 2018, Penrose, now working with Daniel Ann, Krzysztof Meissner, and others, had sharpened the search into something more specific. They were no longer just looking for the concentric circles. They were looking for what they called Hawking points, named for Stephen Hawking, whose work on black hole evaporation the prediction depends on. The idea is precise. At the very end of the previous eon, after all matter has fallen into black holes, and those black holes have spent almost endless ages slowly evaporating away, the final burst of energy from each dying giant would be a concentrated release. And that concentrated release, crossing the boundary into our universe, should appear in our oldest light not as a ring, but as a point, a small spot of slightly elevated temperature, surrounded by a faint, warm halo. They went looking, and they reported finding them, multiple candidate points, at a level of statistical confidence they described as roughly 3 sigma, a threshold that in many areas of physics is taken seriously as a hint, though not as proof. And once again, other researchers looked at the same data and disagreed. The existence of warm spots was not the dispute. The dispute was whether their number and their intensity exceeded what an ordinary universe would produce by chance. And once again, the answer turned on how you build the comparison, on what you assume the random universe should look like. A reanalysis published more recently, in 2024, examined the claim carefully, removed certain unusually bright and dark spots from the data, and used a particular model for the temperature variations, and concluded that no statistically significant signal remained, neither the rings nor the points. The fossils, by this analysis, dissolve back into noise. So, where does that leave us? It leaves us with a question that is genuinely open, contested, neither confirmed nor cleanly buried. And I want to be very careful here, because it would be easy to take a side based on how much you want the romantic answer to be true, and that is exactly the trap a careful mind avoids. As things stand, the weight of the analysis leans against Penrose's claimed signal. Most cosmologists do not believe the fossils have been found. That is the honest state of play, and I will not dress it up. But here is what I want you to sit with, because it is the part that should make you stop, regardless of how the statistics finally settle. Look at what actually happened. A serious physicist, a Nobel laureate, took an idea about a universe before our own, and, instead of leaving it as poetry, he derived from it a specific, concrete prediction. He said the previous cosmos should have left a particular kind of mark, of a particular shape, in a particular place, in data we already possess. Then he went and looked. Then other researchers checked his work, and challenged it, and tried to break it using their own methods. That back and forth, that argument over statistics and assumptions and null comparisons is not the system failing. It is the system working exactly as it should. The claim about what came before our universe became a testable claim, fought over in the open with real data. Whether or not the particular fossils survive, the fact that a fossil of a previous universe is the kind of thing that can be searched for at all, in light we can hold in our instruments tonight, is staggering. Sit with that for a moment, because it is easy to rush past in the noise of the argument. Somewhere in the maps of the oldest light, faint patterns are being measured, weighed, and disputed by careful people. And the question they are actually fighting over is whether those patterns are the last visible signals of a universe that lived and died before ours was born. Not a story about such a universe, not a poem about it. A measurable mark, a number you can extract from data and check against what randomness alone would produce. Think about what it would mean to hold a photograph and wonder whether one faint smudge in the corner is the shadow of a world that ended before your world began. That is, in essence, what these researchers are doing, and they are doing it not with intuition, but with statistics, in journals, in public, where anyone can challenge the work. The romance of the question and the rigor of the method are not opposites here. They are pressed together, and the pressure is exactly what turns a beautiful idea into something the universe itself can be asked to confirm or deny. That is the difference between the fringe and the frontier. The fringe makes claims that can never be checked and so never have to be defended. The frontier makes claims sharp enough to be wrong and then submits them to the brutal honesty of the data. The question of what came before the Big Bang has crossed from one to the other. It is no longer a question we are forbidden to ask. It is a question with predictions attached, and people arguing over the evidence. And the rings and points in the oldest light are only one of the frameworks making such claims. The next one does not put a single universe before ours. It puts an endless, restless ocean of them, and it says our entire Big Bang was nothing more than one bubble forming in it. That idea is not fringe either. It may be the most natural consequence of our most successful theory of the early universe, and it is where we go now. Part 8. The process that never started. There is a version of the answer to what came before the Big Bang that is, in some ways, the most unsettling of all, because it does not give you a previous universe that ended so ours could begin. It gives you a process that was already running, that had always been running, and it tells you our entire universe was just one small event inside it, like a single bubble forming in a pot of water that has been boiling forever. To understand this picture, you have to understand a piece of physics called inflation, and you have to understand why physicists came to believe in it, because it was invented to solve a real and stubborn problem. The problem is this: when we look at the oldest light, the cosmic microwave background, we find that it is astonishingly uniform. The temperature of that ancient light is almost exactly the same in every direction, to within a tiny fraction of a degree. That sounds harmless until you realize what it implies. Regions on opposite sides of the sky, regions so far apart that, in the standard story, light could never have traveled between them in the entire age of the universe, somehow ended up at precisely the same temperature. They are like 2 cups of coffee on opposite ends of a continent that are found to be at exactly the same warmth, despite never having been in contact, despite no way for heat to pass between them. How did they coordinate? The standard Big Bang model, on its own, has no answer. In the early 1980s, a small group of physicists, including Alan Guth and soon after Andre Linde and others, proposed a solution. Suppose that in the universe's first tiny fraction of a second, before the ordinary expansion we know, there was a brief but ferocious burst of a different kind of expansion. Not the gentle drifting apart we see now, but an explosive, exponential stretching in which the universe doubled in size and then doubled again, and again, at least 60 to 80 times over, all in a sliver of time, almost too small to name. This burst was driven by a special kind of energy field, often called the inflaton, and here is what it accomplishes. Everything we now see was, before this burst, packed into a region small enough that it could easily reach a single uniform temperature, the way a tiny room comes to one temperature easily. Then, inflation took that tiny, settled region and stretched it to enormous size, smoothing it out, flinging its uniform warmth across the whole sky. The puzzle of the matching temperatures dissolves. So do several other puzzles that had troubled cosmologists for years. Inflation, in short, works. Its predictions about the fine details of the oldest light have been checked against the data again and again, and they match with remarkable precision. This is not a fringe idea. It is, for many cosmologists, the leading account of the universe's first instant. And that success is exactly what makes its side effect so hard to wave away. Because when you look closely at how inflation actually behaves in nearly every version physicists have written down, you find that it does not switch off neatly everywhere at once. It cannot. The same field that drives the explosive expansion is subject to tiny quantum fluctuations, little random jitters, and those jitters mean that inflation ends in some places before others. In a given pocket of space, the field rolls down, inflation stops, and a hot universe like ours settles out of it. But in the surrounding space, the field has not yet stopped, and that space keeps inflating, keeps doubling, faster than the pockets can form. Sit with the consequence of that, because it is genuinely strange. The regions where inflation has ended are like bubbles, and our universe is one such bubble, a place where the furious expansion stopped and ordinary cooling, expanding, structure-forming history began. But the space between and around the bubbles is still inflating, still doubling, and because that inflating space grows so explosively fast, it always outpaces the bubbles forming within it. It never gets used up. It never reaches a final edge. New bubbles keep forming inside it, each one a separate universe, possibly with its own particular properties, all of them embedded in the same endlessly inflating background. This is called eternal inflation, and the picture it paints has a name you have probably heard, usually in a more breathless context than it deserves. It is the multiverse, not as a science fiction flourish, but as what appears to be a direct mathematical consequence of the same inflation that so successfully explains the oldest light. Alan Guth, who first proposed inflation, has put the matter about as plainly as it can be put. If inflation is correct, he has said, then the multiverse is almost certainly real. The two are not separate ideas you can pick and choose between. The multiverse follows from inflation the way a fire's heat follows from the fire. You do not easily get one without the other. Now bring this back to our question, the question that has guided every step of this walk. If our universe is one bubble in an eternally inflating background, then what was here before our Big Bang? The answer this picture gives is direct and quietly overwhelming. Before our Big Bang, the inflating background already existed. It was already expanding. Other bubbles, other universes, may have already formed within it. The process was already running. And before that, the same. And before that, the same again. In this picture, the inflating background does not need a beginning the way our bubble does. Our Big Bang was not the start of everything. It was a local event, the formation of one bubble, inside a structure that was already there, doing what it had always been doing. What we call the beginning of the universe was a beginning only for us, only for our bubble, while all around it the endless boiling went on as it always had. This is a profoundly different kind of answer from the bounce or the previous aeon. Those gave us a before in time, a universe that came earlier and led to ours. Eternal inflation gives us something closer to a before that never began, an ongoing process with no first moment that the mathematics demands. Our universe is not the opening of the story. It is one sentence in a book that was already being written, in a language that had no first word. And our sun, our galaxy, everything we have ever known, sits inside a single bubble among countless others, formed in a process that, as far as the equations are concerned, was never switched on because it was simply always running. It is a beautiful and dizzying picture, and it would be easy to end here with the comforting feeling that we have found the answer, that there simply was no beginning and there is nothing more to worry about. But that comfort would be false, and honesty requires me to show you the crack in it. Even this picture, the one that seems to escape the problem of a beginning most cleanly, does not actually escape it. There is a theorem, a hard mathematical result, that says even eternal inflation cannot be truly eternal into the past. And there is a critique from one of the very people who helped build inflation in the first place that cuts at whether this whole grand structure is even doing science at all. Those two cracks are the next part of our walk, and they are where intellectual honesty earns its keep. Part 9. The crack in forever. It is a strange kind of courage to build a beautiful idea and then go looking, on purpose, for the place where it fails. But that is what the best physicists do, and the picture of an eternal, beginningless, inflating universe has two such places, two honest cracks, and the second of them comes from one of the people who helped invent inflation in the first place. Let us take the first crack, the mathematical one, because it is sharp and clean. We just walked through eternal inflation and saw how it seems to remove the need for a beginning. The inflating background was always there, always running, no first moment required. That is the appeal of it. But in 2003, three physicists, Arvind Borde, Alan Guth, and Alexander Vilenkin, proved a theorem that puts a hard limit on that appeal. The result is technical, but its meaning can be stated simply. Any universe that is, on average, expanding cannot be extended infinitely far into the past. Trace it backward, and the expansion itself forces you to reach a boundary, a point beyond which you cannot continue the history. You run out of past. Notice who one of the authors is. Alan Guth, the father of inflation, helped prove that inflation cannot be eternal in the direction that would have saved it from a beginning. The very framework that seemed to remove the beginning still, by its own internal mathematics, points back toward one. This does not destroy eternal inflation. It complicates it. It means that even the picture most cleverly designed to avoid an origin still hits a boundary in the past. And so the question we have been asking all night does not simply dissolve, it returns. Something still has to account for that boundary. The inflating ocean, it turns out, may have had a shore after all. And so we are not allowed the easy comfort of saying there was simply no beginning and being done with it. The mathematics will not let us off that lightly. The second crack is different in kind, and in some ways it is more serious, because it is not about whether the picture is correct, it is about whether the picture is even science. The challenge comes from Paul Steinhardt, and you should know his position before you weigh his words. Steinhardt is not a critic standing outside the field throwing stones. He is one of the original architects of inflationary cosmology. He helped build the very theory he now turns a hard eye toward, and his concern is this. He argues that inflation, especially in its eternal form, has become so flexible, so capable of producing any possible outcome somewhere in its endless expanse of bubbles, that it has stopped being able to predict anything in particular. If the theory generates universes with every conceivable set of properties, then no matter what we observe in our own universe, the theory can accommodate it. Whatever we see, the theory says, of course, there is a bubble like that. And a theory that can absorb any observation, that can never be contradicted by any measurement, is in trouble, because the thing that makes an idea scientific is precisely that it could, in principle, be proven wrong. This is a profound objection, and it matters enormously that it comes from an insider. Steinhardt is not saying inflation produced no successes. He is saying that the eternal, multiverse-generating version of it may have crossed a line from a theory that makes risky, checkable predictions into a framework so accommodating that it predicts everything and therefore, in a meaningful sense, nothing. A theory that explains every possible result explains no particular result, and if no measurement could ever disagree with it, then believing it becomes a choice rather than a conclusion forced by evidence. Let me make that worry concrete, because in the abstract it can sound like a quibble. Suppose you have a theory that says every possible kind of universe exists somewhere in an endless collection of bubbles. Now you go out and measure something about our own universe, the strength of some force, the amount of some ingredient, anything at all. Whatever number you find, the theory shrugs and says, of course, there is a bubble with that number. In fact, there are infinitely many. Find the opposite number tomorrow, and the theory shrugs again just as comfortably. A good scientific idea sticks its neck out. It says the number should be this and not that, and if you find that, I am wrong. An idea that is equally happy with every possible result has stopped sticking its neck out. It can never be caught being wrong, and a claim that can never be caught being wrong has quietly stepped outside the thing that makes science work. That is Steinhardt's worry, and the reason it carries weight is that he is not pointing at a rival's theory. He is pointing at the grand version of the very framework he helped create, and asking with real discomfort whether it has drifted from physics into something that only looks like physics. Whether or not you ultimately agree with Steinhardt, you cannot dismiss the worry because it strikes at the foundation of what separates physics from a very sophisticated story. I want to pause here and be clear about what these two cracks do and do not do, because this is the kind of moment where it is easy to overreach in either direction. The cracks do not prove that eternal inflation is wrong. Many serious physicists still hold to it, and they have answers and refinements to offer. What the cracks do is keep us honest. They remind us that the most natural-seeming answer to what came before, the answer that appeared to need no beginning at all, still carries a boundary in its past and still faces a hard question about whether it can be tested. The romantic exit, the one where there simply is no beginning and the question evaporates, is not as clean as it first looked. And there is a larger lesson hiding in these cracks, one that reaches back across everything we have discussed tonight, and it is this. There is a world of difference between saying, our best theory cannot yet describe what came before, and saying, therefore nothing came before, or therefore the question is settled. We met that distinction at the singularity, where a broken equation was quietly turned into a claim that there was no before. We meet it again here, where the difficulty of testing a theory is sometimes quietly turned into either an overconfident certainty that the multiverse is real, or an overconfident certainty that the whole question is meaningless. Both of those moves skip past the honest middle, which is that we have several serious, competing pictures, each with real strengths and real cracks, and we do not yet know which, if any, is right. Living in that honest middle is uncomfortable. It is also where the actual science is. So we have now seen three frameworks, three different befores. The bounce, where a contracting universe rebounded into ours. The previous aeon, a complete cosmos that aged and died and became our beginning. And the eternal process, the endless inflation in which our universe is one bubble among countless others, though even that, we now know, hides a boundary and a hard question in its past. Each of these is serious. Each is built by real people with real mathematics. And there is one more, the fourth framework, and it is the most different of all. It does not involve a bounce or an aeon or a bubble. It involves a collision, two entire worlds, drifting toward each other across a dimension we cannot point to until they strike. That collision, this fourth picture says, was the Big Bang, and it is where we go next. Part 10. The collision. The fourth picture of what came before begins with a sentence that sounds like science fiction and turns out to be careful physics. What we call the Big Bang was not a creation, it was a collision. Two enormous objects, drifting toward each other across a dimension we cannot see, struck one another, and the energy of that impact became everything we have ever known. To take that seriously rather than dismiss it, you have to know something about what one of our leading attempts at a complete theory of physics actually says about the shape of reality. In our everyday experience, space has 3 dimensions. You can move left and right, forward and back, up and down. But string theory, one of the most developed attempts to unite all the forces of nature into a single framework, requires more dimensions than that. In its most studied forms, reality has many more spatial dimensions than the 3 we move through, with the extra ones curled up so tightly, at scales so impossibly small, that we never notice them in daily life. They are there in the mathematics, woven into the structure of space, hidden only because they are wound up far below anything we could ever directly probe. And in that richer space, objects can exist that we would never picture. They are called brains, a word shortened from membranes, and the simplest way to imagine one is as a sheet, a surface that extends through some number of dimensions, the way a flat sheet of paper extends through 2. In this picture, our entire observable universe, everything we can see and touch and measure, every galaxy, every star, you, this room, all of it sits on one such brain, a 3-dimensional surface floating within a higher dimensional space. Picture a thin film suspended in a larger medium. Everything we know lives on the film. The extra dimension runs perpendicular to it, in a direction we cannot point to, cannot walk along, cannot even properly imagine, because we are confined entirely to our own sheet. Now, here is the setup that leads to the collision. There is another brain, another sheet, lying near ours in that extra dimension, separated from us by a gap that is tiny by the standards of the cosmos, and yet completely beyond our reach, because we cannot move in the direction that would take us across it. That second sheet has mass, and so does ours. And gravity, alone among all the forces, is thought to leak across the gap between the brains. So the 2 sheets feel each other. That detail about gravity is worth pausing on, because it quietly explains something that has puzzled physicists for a long time. Of all the forces of nature, gravity is by far the weakest, and it is not even close. You feel this every day without noticing it. A small magnet can pick up a paperclip against the pull of the entire planet beneath it. The whole mass of the Earth is losing a tug of war to a magnet you could hold between 2 fingers. Why is gravity so absurdly feeble compared to the other forces? In this picture, there is an answer. The other forces are stuck on our sheet, confined to our 3 dimensions, their full strength bottled up where we can feel it. But gravity is not confined. It spreads out into the extra dimension, leaking away from our brain into the larger space around it. What reaches us is only a thin remainder of its true strength, diluted by spilling into a direction we cannot see. So gravity feels weak to us, not because it is weak, but because most of it is somewhere we cannot follow. And it is exactly that leakage, that spilling of gravity across the gap, that lets the 2 brains feel one another and begin their long, silent fall together. The same property that makes gravity seem so gentle in your daily life is the property that, in this picture, brings 2 worlds into collision. They are drawn together, slowly, almost imperceptibly, across what might be an enormous span of time, falling toward one another through a dimension neither of them can perceive. Let me slow down and take you into that, because it is one of the strangest scenes physics has ever offered. Picture our universe not as the inside of an explosion, but as a calm, enormous sheet, drifting in a darkness that has a direction we cannot face. Somewhere, just beside us, a hair's breadth away in that unseeable direction, another whole world drifts in parallel, a second sheet as large as our own. Nothing passes between the two worlds, no light, no matter, no signal of any kind. Only gravity reaches across the gap, the faintest pull, drawing the two sheets together over ages so long they would make the lifetime of a star seem like a single breath. For almost all of that time, nothing seems to happen. The two worlds simply drift closer, silent, dark, patient. And then, at the end of that long approach, the sheets touch. Not at one spot, but everywhere at once. The entire surface of our world meeting the entire surface of the other in a single instant. And in that instant, the gentle drift becomes an unimaginable release. The kinetic energy of two colliding worlds floods into our sheet, everywhere simultaneously, igniting it into a hot, dense fire that begins, at once, to expand and cool. From the inside, on our brain, that release would look exactly like a universe erupting from a single hot beginning. It would look like the Big Bang. That is the picture, and it has a name. It is called the ekpyrotic scenario, from a Greek word for a great fire, a conflagration. It was developed around 2001 by Paul Steinhardt, the same physicist we just met turning a hard eye on eternal inflation, working with Neil Turok. Both of them had spent years on inflation and had come to believe it carried unsolved problems, and the ekpyrotic model was their alternative. And notice what it does to our question. In this picture, the Big Bang is not the beginning of everything, and it is not a creation from nothing. It is the moment two pre-existing worlds met. There was, very clearly, a before. Before the fire, there were two brains, drifting toward each other across the dark. Before our universe ignited, there was structure, there was motion, there was a long, slow approach. And in the fuller version of the idea, this is not a one-time event. After the brains collide, they rebound, drifting apart again, and then, over another immense span of time, gravity draws them back together for another collision. Each collision is another Big Bang. Each separation is another long expansion. The universe, in this picture, does not have a single beginning at all. It has a rhythm, a slow heartbeat of worlds, meeting and parting across the unseeable dimension, again and again, perhaps without end. Steinhardt and Turok laid this cyclic version out in their work, including a book whose title says it plainly, that the universe is endless, that the Big Bang was not the start. Now, you might fairly ask whether this can ever be more than an elegant story, and here is the part that lifts it into real science. The ekpyrotic picture and the inflation picture make different predictions about one specific thing, and that thing is the gravitational waves left over from the early universe. Remember those ripples in space that pass through everything, that can cross the wall light cannot. Both inflation and the ekpyrotic collision would have stirred up a background of such ripples in the first instance. But because the two mechanisms are so different, a violent stretching in one case, a colliding of worlds in the other, they predict gravitational wave backgrounds with different shapes. Inflation predicts a particular pattern, with a slight, characteristic tilt across different wavelengths. The ekpyrotic collision predicts a different pattern, much flatter, with that tilt essentially absent. These two signatures are, in principle, distinguishable. If we could measure the spectrum of primordial gravitational waves precisely enough, we could tell which mechanism was at work, and we could rule one of them out. That is what turns the collision from a fable into a contender. It is a minority position. I will not pretend otherwise. Most cosmologists today favor inflation, but the ekpyrotic model is a published, carefully built, peer-reviewed minority position developed by serious physicists with strong records, and crucially, it has not been ruled out. The gravitational wave background that would decide between it and inflation has not yet been measured. The test simply has not been run. And a model that makes a clear prediction and is still waiting for its test is not a failed model. It is a patient one. It sits in the literature, holding its breath, waiting for the instruments to catch up to its claim. We have now seen all 4 of our frameworks, 4 different answers to what was here before, and they cannot all be right. But before we ask how we will ever choose between them, we have to face a question stranger and more disorienting than any of them. A question that threatens to pull the floor out from under the whole investigation. We have been asking what came before the Big Bang. But what if the word before does not mean what we think it means? What if it does not mean anything at all? That is where we go now. Part 11. The word before. Every step of our walk tonight has rested on a single quiet assumption, an assumption so basic that we never pause to examine it. We have assumed that the word before means something. A universe contracts and then bounces. A previous aeon ends and a new one begins. An inflating background was already running before our bubble formed. 2 brains drift and then collide. Every one of those stories needs time to be real, needs a genuine before and after, a sequence in which one thing leads to the next. And now we have to face the possibility that this assumption, the one holding up everything, may be the shakiest thing of all. The trouble starts with an equation that almost no one outside physics has heard of, and that almost no one inside physics likes to dwell on. In the 1960s, 2 physicists, Bryce DeWitt and John Wheeler, tried to write down the fundamental equation for the quantum state of the entire universe, the most fundamental possible description of everything at once, combining quantum mechanics with gravity at the largest scale. They succeeded in producing something, an equation, that physicists still study and use today. But the equation has a feature so peculiar that when you first hear it, you assume you have misunderstood. The Wheeler-DeWitt equation, the candidate for the most fundamental description of the universe we have, contains no time. Not a hidden time, not an approximate time, none at all. The variable for time, which appears in essentially every other equation in physics, simply is not there. Let me make sure you feel how odd that is. Every equation you have ever encountered, even informally, has time woven into it. Position changes over time. Energy shifts over time. Particles interact at particular moments. The entire structure of physics, from a falling apple to an orbiting planet, is built on the assumption that time is there, flowing, real, a backdrop against which things happen. And then you write down the equation for the whole universe at its most fundamental level, and time quietly vanishes from the page. This is not an obscure technical footnote. It is the central equation of quantum cosmology, and it has no time in it. Physicists call the puzzle "this creates the problem of time," and it is exactly as serious as it sounds. So, what could it possibly mean? The most arresting interpretation, and the one that should make you sit very still, is that time is not fundamental. That, at the most basic level of reality, time as we experience it, a flow, a passage, a difference between past and future, does not exist. What we live as time would then be something that emerges from an underlying timeless structure. The way certain properties emerge only when you have enough pieces together. Consider temperature. A single molecule has no temperature. Temperature is not a property a lone particle can have. It only appears when you have enormous numbers of molecules moving and colliding together, a property of the crowd, not of the individual. It is completely real. You can measure it, you can feel it, it can burn you, but it is not fundamental. It lives at a higher level of description, emerging from something underneath that has no temperature at all. Time, in this view, may work the same way. Real at our level, measurable, undeniable in our experience, and yet not part of the bedrock, emerging from an underlying reality where it simply is not present. I find this the most quietly unsettling idea in everything we have touched tonight, and I want to be careful not to overstate it because it is genuinely unresolved. But let yourself feel the shape of it for a moment. You have spent your whole life inside the sensation of time passing, the steady slide from one moment to the next, the absolute certainty that there was a before and there will be an after. It is the most basic furniture of your experience, more basic than space, more basic than your own face in the mirror, and the most fundamental equation we have managed to write for the universe as a whole does not contain it. The flow you feel so surely may be like the warmth of a crowd, real and undeniable to anyone standing in it, and yet made of countless small things, none of which is itself warm. If that is true, then the universe at its base is not a film running forward. It is something stiller and stranger, a single, timeless structure, and the running forward is something that happens only from the inside, only for beings like us who are woven into it in a particular way. We are not necessarily watching reality unfold. We may be reality, briefly convinced that it is unfolding. A physicist named Julian Barber has spent much of his life developing exactly this idea, and his position is as direct as it is unsettling. Time, he argues, is an illusion, not in the dismissive sense that it does not matter, but in the precise sense that it does not correspond to anything in the fundamental structure of reality. What we call the flow of time, the feeling of one moment giving way to the next, is, in his view, a feature of how we are embedded in a universe that is, at bottom, a still and timeless thing. There are other versions of this idea too. Some physicists suggest that time emerges from the way different parts of the universe are linked together through quantum entanglement, that the appearance of one moment following another comes from correlations within a timeless whole. Another approach, called causal set theory, rebuilds the universe not from time, but from pure order, a structure in which certain events simply come before others in a bare, relational sequence without any flowing clock behind it. Now bring this back, carefully, to everything we have built tonight, because here is where it becomes genuinely vertiginous. Every single framework we have explored, the bounce, the previous aeon, eternal inflation, the colliding brains, every one of them assumes that time is a coherent thing to apply to the question of origins. They all describe a sequence. First there was a contraction, then a bounce. First a previous universe, then ours. First an inflating background, then a bubble. They all lean on a before and an after, as if those words are solid ground. But if time itself is emergent, if it is not part of the most basic layer of reality, then the question what came before the Big Bang may not be a question with a hidden answer. It may be a question that quietly falls apart, not because the answer is unreachable, but because the question itself is malformed. Stephen Hawking offered a comparison for this that has stuck because it captures the strangeness exactly. Asking what came before the Big Bang, he suggested, might be like asking what lies north of the North Pole. The question sounds perfectly sensible. It has the grammar of a real question. North is a real direction, and you can keep going north for a very long way. But when you reach the North Pole, north simply runs out. There is no further north to go, not because something is blocking you, but because the very concept stops applying at that point. Every direction from the pole is south. The question, what is north of here, has no answer there, not because the answer is hidden, but because the question has reached the edge of where it means anything. If time emerged with our universe, then before, like north, may be a direction that simply runs out as you approach the beginning, and asking what lies beyond it may be asking for a place that the structure of reality does not contain. I will be honest with you about where this stands, because it is not settled, and I will not pretend it is. The fact that the Wheeler-DeWitt equation has no time is genuine, and it is telling us something real about the universe at the level where quantum mechanics and gravity meet. But whether it means that time is fully emergent, or only that our description of it needs fundamental repair, is something the field has not resolved. What I can tell you is that the honest answer to every question we have asked tonight has to carry this shadow alongside it. Each framework, each bounce and aeon and bubble and collision is built using time as its scaffolding, and the most fundamental equation we possess is hinting that the scaffolding may not be holding anything up. We came here to ask what was before the beginning, and we have arrived at a stranger place where we must wonder whether before is even a real direction or only a story our time-bound minds cannot help but tell. It is the kind of question that feels brand new, the frontier of the frontier. And yet, remarkably, it is also one of the oldest questions our species has ever asked, and long before anyone had an equation, people kept arriving at the same startling answer. That is where we turn now, gently, before the end. Part 12. The old answer. Long before anyone could write down an equation for the quantum state of the universe, long before telescopes or satellites or any of the machines we have leaned on tonight, people sat under the same sky you sit under and asked the same question: what came before the beginning? And something curious happened. Across cultures that had no contact with one another, separated by oceans and centuries and entirely different ways of thinking, people kept arriving at the same answer. Not a scattered jumble of guesses. The same shape of answer, again and again. The universe, they said, does not begin once. It cycles. Let yourself drift for a moment across these old visions, because they have a quiet beauty, and because the pattern in them is worth seeing clearly. In the cosmology of ancient India, the universe moves through immense rounds of creation and dissolution. There is a unit of time called a kalpa, sometimes described as a single day in the life of the Creator, and a single such day runs to something like 4.3 billion years. After each great cycle, the cosmos dissolves, rests, and is born again. And the full span of these cycles reaches into numbers so large they become almost meditative to contemplate hundreds of trillions of years. The beginning of any one world is never truly a beginning. It is always a turning, a re-emergence from something that came before, an inhale after an exhale that stretches across eternities. In the Buddhist tradition, the idea is pushed even further in one specific direction. There is no first cause at all. The question of an absolute beginning is set aside, not as unanswerable, but as the wrong kind of question, a question that assumes something the tradition denies. The universe, in this view, has always existed in some form, cycling through arising and passing away, with no starting edge anywhere to be found. Time has no first moment to point at. The cosmos simply is, and always has been, turning, and in classical Chinese thought, creation is pictured as a movement from unity into multiplicity, from a single undifferentiated source into the structured world we know, order emerging out of a formless whole. One gives rise to two, the two to many, the many to the 10,000 things, the world unfolding from a quiet, featureless origin into all its complexity. If you translate that into the language we have been using tonight, the parallel to a featureless early state expanding and differentiating into structure is not difficult to see. There is one more thread here that is almost too neat to leave out, and it reaches back to something we already met tonight. The ancient Greek thinkers known as the Stoics held that the cosmos passes again and again through a great fire, a universal conflagration in which everything dissolves back into a primordial flame, only to be reborn and run its course once more. They had a word for that fire. The word is ekpyrosis. And if that word sounds familiar, it should, because it is the very name the modern physicists chose for their colliding brains model, the ekpyrotic universe, the picture of two worlds meeting in a burst of fire that becomes a new beginning. The physicists did not borrow the Stoic cosmology. Their model stands entirely on its own mathematics, on extra dimensions and gravity and the behavior of brains. But when they reached for a name to capture a universe born from fire and destined to burn and begin again, they reached back across more than 2,000 years to a word the Stoics had already worn smooth. That is not evidence of anything about the cosmos, but it is a small, human reminder that the questions we are asking with satellites and equations are the same questions people have been turning over by firelight for a very long time. Now, I have to be very careful here, and I want you to hear the care, because this is exactly the kind of moment where it would be easy to say something untrue and let it feel profound. None of these old visions is evidence. Not for the bounce, not for the previous aeon, not for any of the frameworks we have walked through. The ancient thinkers were not doing physics. They had no equations, no data, no instruments. They were doing something else: philosophy, contemplation, a careful reflection on existence, and the fact that they arrived at cyclic pictures does not make those pictures scientifically true. The bounce stands or falls on its mathematics, not on its resemblance to a kalpa. Loop quantum gravity does not become more correct because an ancient text imagined the world dissolving and reforming. The math has to do that work entirely on its own, and it neither needs nor receives any help from these old stories. I would be misleading you if I dressed up coincidence as confirmation, but the convergence is still worth naming as a fact about us rather than a fact about the cosmos. Here is the genuinely interesting thing. Cultures with no shared texts, no common language, no way to pass cosmological ideas to one another across the distances involved, kept reaching for the same structural intuition that what looks like a beginning is really a transition, that the cosmos has no true first moment. And then, thousands of years later, physicists, with their equations and their satellite data, spent decades building frameworks careful enough to take the same question seriously, and when they arrived, they found certain ancient traditions had already sketched the same rough map in a completely different language, with none of the same tools. There are two honest ways to read that, and I will give you both rather than pretend one is obviously right. The first reading is that human minds, when they sit with the question of origins long enough, simply tend to find cyclic answers, because cycles feel complete and self-contained and satisfying, and that this tells us something about how our minds work, not about how the universe works. We are pattern-seeking creatures who find beginnings uncomfortable, and a circle soothes us. The second reading is that the question itself has a structure that pushes careful reasoning towards certain conclusions, that when you follow the logic of origins honestly, whether with contemplation or with calculus, it resists the idea of a true beginning. And both the ancient thinkers and the modern physicists were responding to that same pressure from the problem itself. Neither reading can be proven. That is part of why the convergence is interesting rather than decisive. It does not settle anything. It just raises a quiet, honest question about whether the pattern is telling us something about the universe or something about ourselves. So let the old answers sit beside the new ones, not as proof, but as company. For as long as there have been minds to wonder, the wondering has tended to circle back to the same shape, the suspicion that the beginning was never really the beginning. The difference now, the thing that separates us from every generation that asked before, is not that we have a better intuition. It is that, for the first time, we are building machines that might actually let us check. The contemplation has company, at last, in the form of instruments. And that is where our walk ends tonight. Not with an answer, but with something almost as remarkable, the first real tools for reading what the beginning left behind. Part 13, Reading the Ash. Here is what we can actually say tonight, after walking all this way, and it is worth stating slowly. The Big Bang is a boundary, not a beginning. The oldest light we can directly detect comes from 380,000 years after the event, and beyond that wall, our telescopes fall silent. But the physics does not fall silent. The equations keep running backward through the wall, and every serious framework we have for extending them, the bounce, the previous aeon, the eternal inflation, the colliding brains, arrives at the same basic result. Something was here before. Not nothing, not an absence. Something with structure, with physics, with a prior state that became the fire we call our origin. Think of what that does to the picture you started the night with. The brilliant point of light in the dark, the absolute beginning with nothing behind it. We can now see that picture for what it is. It was never a photograph. It was a story told at the edge of a broken equation. And a broken equation, as we said early on, is not an answer. It is the edge of the map. For a long time, we treated that edge as the boundary of reality itself, the place where being simply stopped. But the edge of a map has never once, in the whole history of our species, turned out to be the edge of the world. It has only ever been the edge of our drawing. And tonight, the edge of the map is exactly where the new instruments are aimed. Consider what survives from before, even when the light does not. After a building burns to the ground, you cannot see the building anymore. But the ash is there. The chemistry of what happened is written into the residue, the pattern of the char, the traces left in the ground. The fire does not erase the past. It transforms it into a record that a careful investigator can still read. The universe works the same way. Whatever existed before our beginning, whatever bounced or aged or inflated or collided, did not vanish without a trace. It left a residue, encoded in the curvature of space, in the faint patterns of the oldest light, and above all, in the background of gravitational waves that crossed the wall light could never cross. We cannot see the building that stood before. But the ash is real, and it is all around us, and the only question that remains is whether we can learn to read it. And here is the part that I find genuinely moving, the part that makes this our moment rather than just an old question retold. For the first time in the history of any people who have ever lived on this world, we are building the instruments to read that ash. Remember that the wall is only a wall for light, and that gravitational waves pass straight through it. We are now constructing machines to catch them. There is a mission called LISA, a gravitational wave observatory, that will not sit on the ground, but will fly in space. 3 spacecraft arranged in an enormous triangle, each side of it about 2.5 million kilometers long, trailing the Earth around the Sun. It was formally approved by the European Space Agency in early 2024. Its builder was chosen in 2025, and it is planned to launch in the 2030s. Out there, free of the trembling of the Earth, it will be able to feel ripples in space that no ground-based detector can reach, including, potentially, the faint background left over from the universe's first instance. There is more being built. On the ground, an enormous next-generation detector called the Einstein telescope is being planned in Europe, with the candidate sites under study now and a decision expected within the next year or two, aiming to begin its work in the following decade. It will be sensitive enough to hear signals our current detectors cannot. And it is not only gravitational waves. The oldest light still has secrets we have not fully read. A set of instruments is now studying that light with a precision that the earlier satellites could not reach. One of them, an array of telescopes high in the dry mountains of northern Chile, called the Simons Observatory, is already at work, watching the oldest light for the faint imprint that inflation, or its alternatives, would have left in it, and it is being expanded as we speak. Others, planned for the years ahead, will push that precision further still. Each of these is, in its own way, a machine for reading the ash, for testing which of our 4 befores left the record we actually find. And remember the puzzle of dark matter, the unseen substance that makes up most of the matter in the universe, that we know is there from its gravity, but have never identified. One candidate for at least part of it is a population of black holes formed not from collapsing stars, but from the density of an earlier era, perhaps even relics that survived from before our beginning. If such primordial black holes were found in the right amounts, with no ordinary way to make them, that too would be a signal worth holding up against the cyclic pictures. The searches that constrain where they can hide are tightening year by year. Piece by piece, the tools are arriving. Let me be clear and honest, because that is how we have walked the whole way, and I will not change at the finish. No single observation has yet confirmed any one of these pictures of what came before. The gravitational wave background has not yet been measured at the precision these models require. The patterns in the oldest light remain contested. The primordial black holes remain, for now, a possibility rather than a discovery. We do not know which framework is right, or whether the right one is even among the four. And underneath all of it sits that most unsettling possibility, that before is not quite the real direction we imagine it to be. I am not going to tell you the mystery is solved, because it is not, but I will tell you this. We have moved, in a single generation, from a question we were told was meaningless to a question with predictions attached and machines being built to test them. That is not nothing. That is the sound of a sealed room turning out to have a door. So let the old certainty go gently, the way you would set down something you have carried a long way. The beginning was not the beginning. It was a boundary, a surface, a transition, and on the far side of it, the mathematics insists something was here, not as a metaphor. As a result, agreed upon by 4 different frameworks that agree on almost nothing else. We are not the first layer in the record. The record runs further back than the beginning, older than the oldest light, and for the first time, we are learning to read what is written there. We may not finish the reading in our lifetimes, but we are the ones who picked up the page. And somewhere out there, in the faint ripples crossing space tonight, passing through this room and through you without a sound, the universe before ours is still speaking, in a language we have only just begun to understand.